Okay. Okay. I think we should be live. I have my like live stream dashboard up over here, and I just want to check just to be sure. Okay, beautiful. It's live. Sorry for the inception there. But I wanted to take a look for a second. Anyways, you know what? Here, wait. So I have like my like little thing open. This is like the Mister. This is the Mister Computer like selection, and I wanted to look at what these cores were. So like, which Mr. cores support CRT analog output. The vast majority, clearly, clearly not, because I've tried a couple of them, and they do not work, like almost ever. Like, yeah, some cores don't work. Hooked up to my CRT. I'm with you right there. Like here, wait. What if we try like, I don't know, what's a good computer? Apple II? Where's the Apple II? Apple IIe. Beautiful. There it is. Let's make sure the display is. Ooh, I can make the display like amber or green. MISC, custom color palette, system and BIOS, audio, video, stereo mix, pixel clock, low res text, scale, the integer, narrower, wider, normal. Okay, aspect ratio, marginal, scan doubler. Oh, we do not want that, do we? Okay. Oops. Low res clean, pixel clock. Ooh, wait, normal makes it clearer. Stereo mix. Okay, hardware. Nope. System and BIOS. Yeah, we want NTSC because as you can see, PAL mode will mess up the VSync. Color palette. Yeah, I guess NTSC display. Color is fine. Do I have a basic ROM? System. I guess not. Nope. Okay. Well, I was poking around at these like, computer. Oh, wait, I have other mount points. Here. Okay, let's just leave this core. Let's go to like, can I do an Atari 800, I wonder? It's making noises at me. And I'll say, you guys can see it fine. Like, it looks great on the capture card, but it's like scrolling on the video. Oh, that's odd. It didn't stop. Print hello. Hello. Okay. 10 print hello from Atari 800. 20 go to 10 run. Okay, so I can do simple demos like that. Here, let's see. Interlace hack, weave, bob, disabled. Because right now it's like rolling on my monitor, even though I have video set to NTSC mode. Maybe I have to cold reset or something. Oh, Okay, it looks like it works now, although it looks awful for you guys. Whatever. Anyways, I'm goofing off. It says Commodore 64. Let's get back to the C64. Dolphin DOS. And I do usually have to go in here too. Change it to NTSC. There we go. Back to it's lovely, familiar goodness. A little basic prompt we have here. So I wanted to pick up where we were yesterday. I said we were doing leak code. We still are. We're definitely doing leak code. But I got sort of enchanted working on something. So let's go back. Neat. Contains duplicate. Okay. This is the question that neat code wants us to do first. This is, I think, the first of the neat code 150. Is it? Yeah, that's the first. Okay. So the way it wants you to do the way. Oh, oops! There's my live stream. Hello, no viewers. Sad. The way it wants you to do it is like this whole way, but the way I did it is like, okay, imagine I basically like looped through every number twice, right? So I started at the beginning. I started here. Oh. And then I had another pointer here, and it said if A and B are ever the same, you know, it went along, it went along, it went along, it went along. When it got to the end of B, it would bring A up one and bring B back. So okay, let me just explain that. So the way I did it was I would call it like a 2-pointer based approach. So I have 2 pointers at this array, right? The array has a bunch of values in it, and let's say there are 2 5s here and here, or here and here. So the way I did it is I start A at the beginning and I start B next to A. And the way it works is I increment it every single time and I say, are A and B the same? No, 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 no. Got to the end of the array, increment A, bring B to the beginning, and I just like kept scanning. Okay. So I kept scanning through until bring B to the beginning, up, up, up. Are A and B the same? Yes, exit. Okay, that's how I solved this question. Question 1. The contains duplicate problem, which I'll just read it out just to make sure we're clear. Given an integer array nums, return true if any value appears more than once in the array. Otherwise, return false. So it gives you a list of nums, and we wanted to tell it if there are any duplicates in that list. So that's pretty simple. And this is a good way to do it, right? It's very simple. It's just 2 loops. But there are better ways to do it, okay? There's this data structure we have access to. And you know what? I low-key, I don't want any of this to remain. I'm going to rebuild all of this as I go. Okay. Oops. There we go. So... all right. We'll close. We don't need this. Any of this. All right. So let's say this is our list here, right? Let me add another one. And those small blue numbers at the on top. Never mind. There's a duplicate. The small blue numbers, those are like array indices. Okay, so but you'll notice basically we're having to touch every single one of these numbers for every single other one of these numbers, right? So like the size of the list is n. Let's make that bigger. So the size of the list is n, and we had to touch every single one of those n times. So we would actually call this solution big O of n squared, right? And what this means is in the worst case, big O, our solution is going to take n squared, right? So the number of operations it takes is going to be n squared of the, is going to be n squared, where n is the number of items in the list. So in fact, we can make n a nice light blue so as to make it abundantly clear where n is coming from. Like, let's get rid of this. Light blue. And it's like, just overlay it right here. Bam, space, space, space-ish, backspace. All right, it's kind of a clunky display, but it, you know what? It kind of works. It kind of works. Right, so n is the length of the array. So that's how long it would take. But what if there were a way we could visit every item once, and then only ever we'd only have to visit every item once. Okay, so it's very simple. What we're going to do is it's very simple. What we're going to do today is we are going to, let me get back to the main scene. All right, it's going to be very simple. No, implementing a hash map in basic. 20 go to 10. Okay, so it's going to be very simple. What we're going to do today is we are going to be implementing a hash map in BASIC. Okay. BASIC is a computer programming language. It was released in, I don't know when the first version of BASIC, but BASIC for the Commodore 64 was released in 1982, right? So this is an old language. This is like the first language that, like, you know, like my parents' generation might have reasonably learned, like either at school or just at home because they were a weird nerd of some kind. But yeah, we're going to be implementing a hash map in BASIC. So let's get started. What is a hash map? So just in case you don't know what a hash map is, let's go here. So the way we usually think of, let's say, arrays, right? So this is you can think of this as an array, right? The first item is at index 0, the second index 1, 2, 3, etc. Okay. But what if we have some data that's really, really spread out? Like, what if we have this number line here? Okay. Where, and let's make it white. Okay, so take this number line here, 0 to 100, right? So what if our data set is a really wide spread? So what if we have a bunch of data that clusters around here, and we have a bunch of data that clusters around here, okay? So in our problem, right, we're trying to find duplicates. You can think of this as like a counting problem. So in the example it gives us, I'll zoom in real big on the right-hand side here. It gives us 1, 2, 3, 3, right? So if we want to keep track of that, you know, let's say this list is we're just counting. So it'll be 0, 1, 1, and then 2. Okay. 1, 2, and 3. These are our like indices here that we're working with. Right, it's very easy to make an array that's able to do this because the numbers are very small. But like I said, what if we have a really wide range of numbers, right? We have a bunch of numbers clustered at the low end and a bunch of numbers clustered at the high end. Okay, what we want is we want a way to map. And here, let me do the little diagram. No. We'll do. Okay, so what we want is a way to map the index to the count. Okay, we want some way to map these two properties. Okay, So let's take how do I want to go about this? So what we're gonna do is, all right, so we don't have enough space to do an array of 100 cells, right? That's going to create a bunch of empty cells in the middle. So we're going to use this function that maps indices to the count, and we're going to turn it on its head. We're going to add another step inside of here. Okay, we're going to map the index to an array index, and it's not just any array index. It's going to be like a smaller array index, and here is where we'll store our count. Okay, so right here, index, the index is like 1, 2, 3, which we might actually call this a key. So we want to map our key to our value, right? So in this example, it's really easy, where we have the keys are all really low, 1, 2, and 3, and the values are arbitrary. The keys are all really low, but like I said, we might have cases where the values are going to be really wide apart, and we don't want to waste a bunch of empty space. So what if we only have 6 or 7 total values in the array, and we want to map, but they might be 0 to like 10 or 90 to 100 or whatever. So yeah, like I said, we need a way to map the keys to a small array and output a value. What this step is called, this function right here, this is called a hash function. That's what that right there is, and we'll make it green. So we'll take our key, put it through a hash function, map it to an array index, which will finally hold our value. So this is what a hash table is. This is what a dictionary is. We're implementing a dictionary in BASIC. Very, very easy. So we have like our pseudocode, right? We take a key, put it in a hash function, get the array out. That's very straightforward. So how do we implement this in BASIC? Well, BASIC has some main limitations, and let's lay those out. BASIC limitations. Okay, so we don't have dynamic arrays. So we don't have dynamic arrays, right? You declare the size of an array at the beginning, and it can't change. You can't scale it up or down. Even worse, arrays can only hold 256 values. So we're really limited in size here, right? We'd have to chain multiple arrays together or use some kind of like multi-dimensional array kind of structure in order to fit like many keys in our hash map. It's also, right, 8 bits. Commodore 64. It's also slow. So right, these are some major basic limitations. So how are we gonna get over them to implement all this hash map goodness? So I've done some thinking on this, and here's what we're gonna do. I showed, if you watched the last VOD, I did a bunch of work trying to like make the hash function, but I found that it's much simpler than that. So, all right, so let's take a real example, okay? Let's take some data. Our data is going to be okay, nice. I can make it nice and big by default. Anyways, so let's make some fake data. So we have a bunch of numbers. We want it to be 1 numlock 1 1. That's already a duplicate. 1 99 8 95 7 6 and I don't know, 92 91, sure. I mistyped that, but that'll work. 3. And let's put a duplicate in 8. Okay, so let's say this is the input to our counting problem, right? It's wasteful to make an array where we're only using this much, right? It's wasteful, but it's doable, but that's bad. We want to prevent waste. So we want to make a hash function. So let's just pseudocode a hash function for this, right? So we know our values are in the range 0 to 10. And they're also in the range 90 to 100. Okay. Really, we could be more specific here and narrow it down further, but for our purposes, this is good enough. Okay. Now, suppose we only have an array 1, 2, 3, 4, 5, 6, 7, 8, right? Suppose we have actually no. Let's get some better fake data. You know what? No. Okay, but suppose we have an array that's like much smaller. So we only have like a 10 cell array. How do we map these values? Hash function, green, into a much smaller range. We just want it to be between 0 and 10. Or let's say 0 and 9. We only have 10 available cells. Well, an easy way would be you take the value, and let me tweak you just a bit. I changed the value. An easy way would be this function right here, okay? And we can make it medium. All right, let's say hash function. Hash function, or let's use like pseudopython, def hash function. It takes in some key k, and if k is less than, this really just is Python. If k is less than 10, then I just return k. Okay. Else return k minus 90, right? So we just shave off this top digit here with our hash function. We take it and we just go lop it off. We take it and we just lop it off. We take it, lop it off. And now we have a nice set of data that if we have an array with 10 cells, okay, we have an array with 10 cells. Each of these is going to fit in very nicely, right? Our 1 will fit in here in index 1. Our 9 fits in at index 9. Sorry, let me move that up. Our 9 fits in at index 9, or 99 does. So like, we can just draw some arrows and we'll make them green because this is what they've hashed to, right? Our 9 goes into index 9. 8 goes to 8. And, I could keep going here, but you get the picture, right? 1, 2, 3, 4, 5. So that's our hash function. But we have an issue with this hash function. Let's get rid of these guys. This hash function is too stupid. Way too dumb. It's dumb. Gotta go. Because what happens if I want to, like before, instead of being 92, what if instead this is 91? Okay. Well, now we pass it into our function. 1 goes here just fine. But then we also want 91 to go here. That's tough. It's not going to work. This is what we call a hash collision. So this is what we call a hash collision. There is something we want to avoid because it slows down the program, because we have two ways to do it, to fix this. Number one, we can do what's called linear probing, where we see, okay, one's already occupied. So actually I'll go up to the next spot and I'll say, okay, this is my spot now. And then if I get, if 2 comes along, right? So let's say we add, let's add a 2 here, right? If 2 comes along, 2 is going to look at where 92 is and say, okay, it's occupied, so I'll go across, right? And they'll keep going until they find their actual spot. But at every single cell that, these values would have to skip, it's unfortunate because we have to do an equality check. We have to check absolute equality and make sure that we actually have, the actual number there. So this hash function's bad. It's got to go. So what's a better one? Okay, let's return to our basic limitations. Only hold 256 variables. That's a nice power of 2. That's nice, 8 bits. So we're going to use that to our advantage. Okay. So suppose our values are in the range of 16 bits. Okay. We'll say vals are 16 bits. Or no. Vals can be anything. What we're going to do is we're going to do what's called the Knuth multiplier. I don't know if this is what's really called, but I know this is attributed to Mr. Donald Knuth. Is it Knuth or Knuth? Man, I never know. I'm going to call him Knuth. Anyways, what we're going to do is we're going to write a new hash function. Yeah, it can be green. Where, be big. We're going to write a new hash function where, and we'll call it Knuth hash, Knuth hash. Knuth hash takes in a key K, def Knuth hash. All it does, it's very simple, is it multiplies the key. It's very simple. It's a one-line statement. Multiplies the key by some small odd numbered prime. So let's pick 31 here. And then it takes the key and it can logical AND it with 255, right? So if you're curious, 255 is the largest binary value. So I can write that in binary down below just in case we need the reference. 0B 1 2 3 4 1 2 3 4, right? So this is an operation which like chops off all the bits. So this will make our values nice and dispersed and also make them fit within a Commodore 64 array. So why don't we get to programming? Or yeah, why don't we get to, I'll plan one thing. Okay, so we want to be able to interact with our hash map, right? When you interact with an array, you'll do like Excel. You'll do like a at index. We're not going to be able to do that. And I'm not good. I'm not a very good. I don't know basic that well. I'm sure there is a way. Some advanced wizard out there could use, assembly to implement new like ROM functions and I don't know, all that kind of stuff. I'm not going to bother. Instead, what we're going to do is we're going to use subroutines to do this. Or really, here, let's walk before we run. So let's start off by implementing this hash function. Let's implement Knuth hash. Let's implement Knuth hash in Commodore 64 Basic. Main scene. All right. So, like I told you before, it's what? Layer shift clear. Okay. So Knuth hash, it's the key times a small prime, let's do 31, and with 255, right? That's how you would write that in BASIC. But how do you do a function? Well, let's look it up because I don't remember. Basic wiki function. Programming subroutines and functions. Okay. Parameters. No, that's not the right kind of basic. Say basic function. Basic functions, Commodore 64 wiki. Goodness. Function. All right, here we go. All right. Def. We're able to define a function. So let's define the function, or let's be a proper programmer. We can say rem Commodore 64 hash table. And on line, let's just go by tens. I'll say def function knuth hash, or why don't we call it k hash? Takes in an input k. And it equals, it equals parentheses k times 31 and with 255. All right, and let's just print print function k hash on, I don't know, 3. Run 93. Let's print some more. Let's do some more. Instead of line 20, we'll say let's do infinite loop. Print function k hash, and I want to do int random number int, and let's do like 1,000 times random number 1. Yeah, that's lucky good. 30 go to 20. Okay, so this is what our hash function. I'm realizing I don't have it on the screen. I really have to go pee. I'll be right back. Okay, I'm back. All right, so on our screen, we've got just a bunch of random numbers. Let's list our program. Let's do a more meaningful test for I. What's it equal? Oh goodness, equals 0 through to, let's just say 10. I'll say print function, or here, let's make it shorter. Function k hash I. Next. Run. So we can see that the numbers 0 through 9 all give very, very nice, very nice spread out values that are all, none of them are colliding with each other. And I want to test something real quick. Let's say, let's our program. Let's say it's equal to negative. Oh shoot! What on earth? Right. Oops. Okay. Space negative 1 0 space negative 10. Run. Okay. Beautiful. Okay. So yeah, the numbers are nicely spread out. The negatives don't collide. 0 is still 0, but I don't think that's actually going to be a big deal. But yeah, let's go and do this. So, all right. So what you just saw here, we look at this program. All right, basic is weird. All right. Let's think about like other languages for a second. So this is some like Python syntax, right? To define a function, you say def Knuth hash, like you def function name, function parameters, and there's really advanced function parameters and stuff. Basic doesn't have functions like that. Okay. Basic has like these def functions, right? So line 10 here, this def function k hash, and I can highlight it. 10 def function k hash. That's like the only way. I'm not kidding you. This is literally the only way to do a function in basic. And real quick, I have my laptop on the side. I don't know why I haven't had stream open. The odd viewer joins. I'd like to be able to say hello. I need chat open for that, but it was my laptop died, and I had to charge it. Man, I never charge, because here's the thing. I've got like 3 laptops that I use on a day-to-day basis. Okay. I've got my work laptop, I've got my Mac, which I had from school, and I have my like laptop, which has like a graphics card. So I play games on it, I stream on it, stuff like that. It's Linux, but my work and this one are Linux. But I use Arch on this one, I use Fedora on that one. But yeah, so I have these 3 laptops, and I almost never charge my Mac because I'm just never on it these days. That's kind of a lie. I am on it pretty regularly, but it's not really been something that I don't know. I've just been on my other laptops a lot more because I have a reason to be on them, and I also don't love Mac OS. It's definitely better than like Windows, of course, but still, it's not ideal. And oh gosh, I'm gonna like die if I go to live studio and I'm not live right now. Wait, I already saw it on the other one. What am I saying? I'm like tripping. Okay. Anyways, okay, I have a chat window open now. All is well in the world. I'm able to see stuff. Sorry if my audio was bad there. I was turning away from the mic. Anyways, yeah. So Commodore Basic, it has these functions. All right. When you say def fn, all right, you give it a name. You give the function a name, and you name the parameter. All right. These functions can only return numbers, and they can only input numbers too, I think, which means that there's actually a restricted set of things that you can call within them, right? So you can call random, you can call, add, multiply, divide, subtract, exponentiate. Here, let's see if there's, I think I had a list pulled up. Def, yeah, absolute value and whatever ATN is. Oh, arctangent, the inverse tangent, your like trigonometry operators, and you can call other functions, of course, too. What is FRE? FRE. Oh, interesting. What does it do? Here, wait a second. FRE 10. What? 10.0. It's not working. Print. Oh, I have to print FRE 1.0, 1.9, and it gave me -2 something. I have no idea. Okay, FRE accepts any numerical argument within the limits of the floating point format or any string argument and returns the number of unused bytes of basic RAM. The argument has no influence on the result. Okay. So that's just the number of free bytes of RAM. That's pretty cool. anyways, as I was saying, basic functions, like I define here, right? Def fn k hash, it can only return a number. Okay, so suppose I want to do more than that. Well, we've been doing it. We've been doing it some way, right? So let's say I have a little like routine I want to make, and I'm already sort of giving it up because I told you I use the word routine, but I have also this thing called a subroutine. Okay, and we don't need a keyword to do this, right? We can just use basic. We can say like, let's pretend like lines 30 through 50. These are my subroutine. Okay, so on line 30, I'll define my input variable. I'll say a equals, oh gosh, oh, it's over here, equals, also I'll initialize this -1. I want to say 40. I want to print a, give me a to the power of 2 and 50 brk, or not brk, is it ret? How do I return from where I did a go to? Oh gosh. Oh man, my complete lack of basic knowledge is not, it is not, you know, good for me. Go to, I know there's a way to do it, right? Where like you go to somewhere and then you can like go back, I think. Go to line anomaly. Go to 30. Hmm. Where is it? How do I leave my go-to? Okay, let's pretend like I don't know how to do that. Okay. Let's go back up to line 30, because, or you know what? We're not even pretending. I know how to do it. We'll say L equals, or I don't know how to do it. Whatever. Equals -1. Okay. And I want to say 50, go to, or I'll call it R. Okay. So I've sort of defined a subroutine here where I can use it in the program, where I can say right above it, I can say it line 29, skip this, go to 51. Okay, so this is a subroutine, go to 51, we don't care about you. Well, I can say, suppose I want to use this print number to the power of 2 function. I can say, I can start my program in line 60. I can say print welcome to my program. And then I can say, I can do my input. All right, I can say a equals, let's say 10, and I want to return to, I don't know, let's do infinite freaking, or just go to the next line, line 80. We'll say 80. Oh, r equals 10, r equals 80. Go to 40, right? This is where our program really starts. Line 80, a equals 3, return to line 90, go to 40, right? This go to 40, we can think of it as like a function call. And line 90 will just be print, thank you, undefed statement, error in 29, oops, let's be more specific. Go to 60. So it prints that error in 50. Go to R. List. Can I not do dynamic go-tos? I don't think you can use variables for go-tos. Okay, well, I've been talking out of my butt. Here, wait. Dynamic go-to in basic. Commodore 64. Yeah, wow, not natively supported. Oh well. Okay. Well, cool. Let's just do Commodore 64 subroutine. All right, let's just be realistic here. 29, 30, 40, 50, 60, 70, 80, 90. Bang, bang, bang. Okay, so here's our program, right? We've listed our K hash. Let's do some subroutines. Okay. Go sub. All right. So go sub is a basic command, right? So in Python, let's say this is Python. All right. So I could say like I could just call K hash with K, but we've already seen up here where it says print fn K hash. In order to call the function, we have to specifically say fn K hash. Well, in here we're going to be doing unnamed subroutines, I think. Yep. It looks like in this little example here, the way it does a subroutine is it'll say like 30. It just says rem put into hash table. Okay, so like we would do something like that, and then we'd say like line 40, I don't know, print hello, and then we could say return, and we could say go sub 30, run our program, and we get our print, and then it says return without go sub, error in D. Oh, is it end? Subroutine at the indicated line number. The call is placed into the stack. Okay. Let's I guess at line like 25 we'll end. Huh. Oh, I guess we'll want to on line 21 go sub 30 run. Okay, so yeah, so it prints and then goes home. So let me clean this up. All right, so this is our program, right? Over here we have like a remark, a print, and then a return, right? So you can think of this as like function name, function body, return from the function. And this return, it does not return a value, okay? It returns you back to where you were in the program. So I call this subroutine here by saying go sub 30. Okay, so it goes to 30, says, okay, this is a function name, whatever, I'm ignoring that, prints, and then says return. All right, so we were on line 21, so we'll go back up to line 25, then the program ends. Okay, so that's how a subroutine works. So we're going to write some subroutines, I guess. You know what, let me also clear all these lines. All right, beautiful. So, all right, we need to define our API for our hash table. So just to keep things simple, we're only going to have one hash table. And we'll say we can put hash, put an item into a hash table, and we can get an item from a hash table. And yeah, that'll be it. So why don't we, here, we'll define our hash table on line 2, or we'll say HS or HT, hash table equals dim 255 or 256. Is that blasphemy? Syntax error, yeah, okay. 2HT equals dim 255. Right, so what this does is it makes a hash table that is 255, or it makes just an array that's 255 cells, you know, wide, big, I don't know. You might be asking, well, Patrick, why'd you name it HT? Here's a fun fact. Basic variables can only be 2 letters long, right? So you can put several letters afterwards. Basic will only care about the first 2 letters, which is just insane. That's just insanity. Whatever. So we've defined our hash table up here, and then we're going to define our program put hash and get hash way down below. So you'll be like line 1000, or honestly, yeah, you'll be line 1000, you'll be line 2000. Okay, so why don't we say 1000 rem get put into hash table. Line 2000 rem get from hash table. Okay, let's say for now, let's say that these both just take ints. Okay, we'll take in an input called capital I, right? Or, you know, everything in, there's no capitals in basic. So yeah, they can share an input variable. So why don't we just say, like, I don't know, 999, or honestly line 3 I equals 0. Okay. Or honestly 3 empty, 2 HT equals dim 255, bam, I equals -1, bam, rem HT vars. Okay, so the program, we tell it what we say what it is, we define the hash table like input variables, right? Because we don't have functions, we have subroutines. So all the variables are global, and we just have to be very careful. We're just gonna pretend like HT and like I are, you know, inputs to functions and not actually just global variables that we can use anywhere in the program. So let's keep going. How long is it? Okay, 54 minutes, perfect. So, all right. put hash, the way put hash is going to work, honestly, these should be separate things, but we can worry about get hash later. So to put an item into our hash table, it's going to follow a basic structure where, you know what, I guess it's dependent on get hash. So actually, let's I'm trying to think of how best to do this. Because all right, here's my dilemma is that, right, hash tables are okay, so like, suppose we want to do, I explained it earlier, this like linear probing that requires us to keep in mind which number went where. So we actually would need like a second array that has the key the cell corresponds to. So, oh, oops. You know what we might do, oopsie, there's my little Python script. We'll go here, we'll list again, and on line 2, instead of just declaring ht as, you know, 255, what if we say it's 2 by 255? Okay, and then, all right, really it should be 1, because that's like the max index. Yeah, you know what, Commodore 64 dim. Allocate space and array memory for a new array. And these are real numbers. But honestly, we only need ints. But whatever, it doesn't matter. It doesn't matter. We have a one-dimensional array. Size d1 by d2. N plus 1 variables. Right, so yeah, so it'll be indices 1 and 2, or 0 and 1. Okay, so let's go back to planning. Okay, so we'll have this hash table, and let's bring these guys down even further. So we have our array. We've got ht, which ht 0 I, ht 0, and we'll just say like x is going to be the keys, and ht1 x is going to be the vals, because then we can support linear probing, right? Because like up here, if we get a hash collision like 91 and 1, you know, on this, you know, in our silly subtract 90 hash table, whenever we do 91 and 1, we need to have a second hash table over here that stores 91 over here. That stores 1 in 91, so that it knows that it's like properly probing. So these are actually keys, and you're actually vals. All right, so that's very simple. We'll use a multi-dimensional array for this. Okay, so get hash. Oh, can you do nested subroutines in BASIC? Oh gosh. I think so. We're going to pretend, we're going to assume we can and hope for the best. But okay, so let's keep let's keep let's keep working on our hash function. So get hash. All right, all it's going to do is look up okay, so yeah, it's going to look up, let's write this in a list. Medium, it can be like blue. Step 1, find the key at k hash of I. If not the key, go to the next cell. If key, return the val at cell index. Okay. So here's how it'll work. So let's go back up to our diagram here. Let's delete a bunch of this. Oops. Let's just delete a bunch of this stuff because we don't need this for explainer purposes anymore. Bye, and bye bye. Okay, yeah. So let's suppose that this is the actual contents of our hash table, right? So we'll start off by it says find key at k hash of I of our input, right? So we'll hash our input. So we have our value. It hashes our input to here. Okay. It says, oh, this seat's taken, right? The key is not equal to 1. So it goes to the next cell until it works, right? And it'll just keep going from here. Bop, bop, bop. So yeah, that'll be easy to implement. So we'll be able to do that. So all right, 1010. It'll say key index equals function k hash on I, right? We're assuming that we have, or no, this needs to be 2010. Ki equals fn of k hash. And then we'll say 2020 for and oh, you know what? We need a return variable. Let's say 2001 get return equals oh gosh, equals -1. Okay, let's clear this, just list. So all right, so we've defined our return variable is gr. So all right, in the order of the program. Okay, we've done step 1, right? And I can open up Excalibur over here. Okay, we've done step 1, find key at k hash of I. Now we just do step 2. 2020 if ht at 0, because 0 is our keys, right? So if ht at 0 comma ki equals if it equals I, right? Because it contains the keys. So if it equals the input, then let's go to like 200, right? This will be our return. 2200 will be get return. It should be equal to ht at 1 comma ki, and I guess we'll use ki here as our, you know, incrementing as our variable to keep track of things. Okay. And okay, this is one weird thing about basic, right? So you've seen me typing in line numbers this whole time. This means that I can type lines completely out of order. And that's what I've just done, right? I'm going to keep going on at line 230. So like if they're equal, then we can just return. But otherwise, what we want to do is go to 2030 and say for, and I'll say I equals 0 to 255, 2040. So if it's not the key, then go to the next cell. And we already know that we'll need to check the next one. So we'll linear probe and say if ht 0 comma ki plus I, right? So the key that we're at plus this like linear probe. Oh, and oh, here's something we'll have to do. Ki plus I. Oh gosh. Ki plus I and 255, right? We have to clamp it down into the range that it'll fit in our hash table. Okay, so if that is equal to our, what's it called? Our input variable, then how do if statements work on the Commodore 64? I forget. Let's say if equation, then line number. Okay, so that's all we get. So yeah, if this is true, then we want it to go to then I don't know, go to what if we say like 2199 and we say 2199 is going to set gr to, right, it's going to set it to this thing we just calculated, our hash table on the val table with ki plus I and 255. And oh gosh, I need to count parentheses. 1, 2, 3, 1, 2, 3. Yeah, okay. And then on line 2210 will return, right? So here, let's get some clarity here. Let's because I've been just haphazardly throwing in lines wherever I feel they fit. So okay, so here's our subroutine. Starting at line 2000, get from hash table. So we declare our return variable. We do step 1, and here I'll get the Excalibur back up. We do step 1, find the key at k hash of I, and then we find k hash I, and then we say if the hash table at k hash of I is equal to the key, right? We have our keys table, we have our vowels table. If it's equal to our key, right, then we have a match. Then just go down to line 200, which is down here, which sets the hash table to, which sets the return value to ht at ki, ht1 at ki, to our vowels table. So it just returns the value, and then it continues on. Otherwise, it's going to keep going, and it's going to say for I equals 0, or it should say 1. For I equals 1 to 255, so it's going to loop through all those values. This, it finds the, it goes to the next cell. If the key, right, keys table, ht at 0, is equal to I, the input key, then it'll go to 2199, which sets the return value. Oh, it's delightfully wrong. 2199. What you should actually do is set ki to be ki plus I. Or ki plus I. Ki plus I. And 255, right? So it goes to 2199, which sets the key, and this is kind of a fudged use of the variable. It sets the key to the right thing, sets the return variable to the value, and then returns, right? So that's how we're going to get items out of our hash table. You know what? Let's do something manual real quick. Let's list. Let's say on line 20, I'll say ht at 0, 0 is equal to, you know what, let's make it equal to not 2. Okay, so our first key is going to be 2. And honestly, what's real? Let's add another, and let's just assign the value here as well. 1, 0, oops. 1, 0 is going to equal 2 should map to 5 for some reason. I don't know. Okay. Now, man, I don't know how to manufacture a hash collision. Actually, you know what? Let's just clear all that and keep working. So this should be able to put items into a hash table. And actually, you know what? No, that's what I wanted to do. Also, I'll say on line 20, I want you to say ht at function k hash of 2, right? Should equal, and really ht at 1, or ht at key table 0, 0 k hash 2, or function call k hash 2 should be equal to 2. So we'll set the key, and then we'll say ht1 function k hash 2 equals 5. Okay. In theory, going to line 30 and saying we'll say, what is it, gr, or no, yeah, get return, or no, we'll say input equals 2. So we want to input a value into the function, and then go sub to, what's the line number? 2000. And then line 40, I just want to print the return value. In theory, okay, let's list it just so we can read it out one more time. Okay, we define our hash table, we define our hash function, and then we set a hash value manually, right? We don't have a put function yet. So we say the key is 2 with the hash value 2, right? And then we say the value, again, hash value 2 at the same spot, but in the value table is going to be 5. Then we say we want to input the variable 2 and go sub 2000, right? We're not doing a function call. So we're sort of simulating function inputs or like procedure inputs. So 2000, we're getting from the hash table. Ki is k hash at I, okay? If 0 at ki equals I, then it should go to 200. This is the code path I think we'll follow, where it'll set the return value to the hash table at the key it just found and then return. Okay? All right. Syntax error on line 2. Okay. That's actually good. I don't know what the syntax error is. Let's try this. Run. Syntax error in 2. Okay. ht equals dim1 255. And then we set I equal to -1. Oh, and maybe here, I think we have to say like 998 and run. Error in 2. Okay, that wasn't the issue. ht equals Tim here. Why are you mad at me? Let's try it one statement at a time. Just run. Syntax error in 2. Okay. Am I not? Oh, I don't think I'm doing the dim correctly, am I? Yeah, nope, I'm dumb. I'm dumb. We want to dim 1 dim a 1 255. And then we can say I initialize it to some dummy value. All right, now we can run. Okay, anyways. Bad subscript error in 20. Okay. What's wrong? 20 ht 0. Do I have to like put it in parentheses? Or do I have to like, I'm gonna have to like juggle all of these. Like it would have been better programming style to make it a variable in the first place. Bad subscript error 2. Okay. So let's retype line 20. I'll say 20. I'll say A, or no, I already. No, wait. Here's an error that I made. HT. Try that. Oh my god, it printed 5. It printed 5. No way. It printed 5. It worked. Oh my god, it worked. Holy crap, it worked. Oh my gosh. I feel like I just witnessed a miracle. Wow, okay. Anyways. Well, awesome. Okay, that's pretty cool. Shoot. Wow, man, that feeling never goes away. I'll tell you one thing. The feeling when you're programming, whenever you run the code and it works, for the first time, it works, right? It doesn't matter, isn't it? Okay, running it and it works on the first time, that's magical. But running it the very first time you write a program and it works, that's amazing. Wow. That's so cool. Anyways, let's all right. Let's get back to the mission at hand. Okay. All right, put hash. It's basically the exact same thing, except instead of returning the value, we're just going to put the val at the cell index. So, in theory, okay. So in theory, what we could do, and you know what, I might just do this. I'm going to use a secret value. Okay. So, right. So if we look at our like pseudocode again, it's got like, these are basically the same steps. So it's going to be basically the same code. The big issue is, we're just, the issue is that, no. Okay. I'll tell you what I was thinking. My plan was I was going to like have get hash also return the like true index, right? Like after resolving hash collisions, I was going to return the actual index inside, what's it called? Inside this array, like this index, not the key. But I don't think we should expose that even incidentally. So we're just going to repeat some code. Okay. So I'll say 1001, or honestly, no. Can I do something like this and just say, we can start off, just by like duplicating all of this. List. Yeah, okay, we can. And then it just duplicates all of that. Instead of gr, what we want to do is pr, put return. Ki is the function at k hash of I. If ht 0, so if the key is equal to I, then 1200. And line 1200, it should say oh wait, put needs to have 2 input values. So let's, oh gosh, can I like list like a range? Oh, how do I list a range, man? What the hell? Okay. List. This is an esoteric. Okay, I can say list. Give me the first 100 lines. Okay. Yeah, line 2, we want to add like a second input. IA equals -1. Okay. So we've added a second input. So the key is an I. Say key I val IA. And that's highly cryptic. Get from hash table. And I'll say key I, right? I've had to define a whole new global variable in order to keep track of all of this. Oh man, what a mess. What a mess. Man, it's so easy. It's got to be so easy. And I'm experiencing right now. It is easy to write spaghetti code in basic. Wow. Okay. Okay. Let's keep going. Okay, so we get the keyed index, the hashed value. And then if the hash table doesn't have a spot, or if the hash table it equals the key, then go to line 1200 where we want the hash table at ki to equal the value input. And that's the only change we want, actually. So that still gives 5. Give me the first 100 lines again. Ooh. List 100. Oh, 199, that's fine too. Okay, so instead of doing this whole rigmarole, let's say 20 I, the first input, equals 2 IA equals, oh goodness, equals 5. Go sub to, or 1000. And real quick, I think I saw, then yeah, okay, so yeah, we actually want this to be 1199, because then down here, 1199, it sets the key properly based on this for loop. And oh, here's something I missed in both loops. 2050, if the if value isn't true, it should just be next I. 1050, next I. It should increment. It should go through all of the whatevers. So okay. So all right. So we list the first 1000 lines. So we have this. Yeah. All right. And you know what? No, I'm not going to bother with that. Or you know what? No, yeah, I will actually. The return value of putting a key inside the table, PR, you should just be the key. Because all we're doing is setting a value in the table and then returning. List the first 999 lines. So, okay, so we put a value in the table, and then why don't we print the key, and then on line 30, we print and then yeah, on line 30, we get the value at 2, and then we print it. Okay, so this should print 2, 5. Okay, so something is 2, hold, 5. Oh my gosh. Wow. And man, do you see how slow that is, guys? Oh my gosh. I did not realize how slow the Commodore 64 was until now. That's crazy. Wait, no way. Run that again. Oh, wow. Man, even though it's working totally fine. Okay, well, you know what? Let's go ahead and finish up our neat code. Contains duplicate. So, right, given an integer array of nums, return true if any value appears more than once. So let's list the first 999 lines, and we can implement as a very simple algorithm that uses this hash table. Okay. Oh my gosh, that's crazy. It's so slow. Oh my gosh, people used to do this every day. This used to be like man, because this was an expensive computer back in the day. Like, wait, how much did the Commodore 64 cost on release. Okay, it cost $2,000 in 2025 dollars. Wow. How much can you get the Ultimate for? Commodore 64 Ultimate. Oh. See, you can get an FPGA Commodore 64, just Commodore 64, for only $324. So it's way cheaper today to buy. Oh man. Anyways. Um yeah, that's crazy. That's crazy. Anyways, we're writing we're doing contains duplicate, right? We're doing leak code on the Commodore 64. Okay. And you know what? I could spend some time going through and optimizing this, but quite frankly, all right, I'll let you know something. I'm learning Commodore 64 Basic because I wanted to go through the manual. I want to learn how to use the machine. Truthfully, I want to go straight to assembly code. I want to learn how to write assembly for this thing. Yeah, that's all. Let's keep going. So contains duplicate. The plan is this, right? For contains duplicate, where we're gonna loop through. Okay, so yeah, so let's look at this list. Here's our plan for contains duplicate. We're just gonna loop through the list and increment the value in the hash table, right? So increment the value, increment the value, increment the value, increment the value, increment the value. Oh, and if after incrementing it's greater than 1, then we can return, right? So we hit 8, and 8 was already over here. So yeah. All right, so let's say, but it's a very simple algorithm. So what we'll do is we'll define our input array. Let's call it A. Let's say like line 11 A, or rather we'll say dim A, and it'll be like what'll it be? Like let's say we have 255. Or really no, wait, let's say yeah, dim A, it should be 255. And then what I want it to do is 12 for I equals 0 to 255. A at I should equal a random number between 1 and 1,000. So really, here at we defined a function on line 10. Let's define one on line 9. We'll say def function rk random kilo or r kilo. And we don't really need an input, but we'll call it I equals R and D, an integer 1,000 times R and D plus 1. And that should do the trick. Oh, no, it shouldn't. We got it. You say random between 0 and 1 as a decimal. And then, yeah, okay. On line 12, we can say, and we're just initializing the array here. We're just initializing it so we can do this problem. And let's start small. I equals 0 to 10. A at I should be equal to R kilo I. We'll pass it in anyways. and then print a at I with no space, or with no space. Okay. Oh gosh, I forgot. List 100 or list 100. Okay. So we define some functions, we define our input array, and then we fill it with random values up to a certain point. And then here, let me clear out some of these. 20, 25, 30, 40. So right now I'm just trying to figure that. So let's do a diagnostic. And just run. Oh. Run. List through line 100. It prints a at I. List 100. For I equals 0 to 10. A at I. Oh, here, let's honestly here. Maybe not. And then it finds a random number and sets a at I to that, and then it should print a at I. Oh, haha. Next. Oh. Oh, that's because I did random at 0. List 9. Okay, yep. How foolish of me. All right, now run. Run. What? Gosh, I do this every single time, man. I wish the Commodore 64 could like read my mind, and then I could, you know, whatever, I could type with it just with my mind, and it could like show me the code. But all right. To 100, do this, and then go next. An R kilo converts to an integer. Okay, you know what? Here, let's just clear line 12. And we'll say 12 for I, or for J. I'm changing it to J because I keep using I in different places. 2, 10, 13, not 23, 13. R value equals R kilo at J. 14, print RV with no space. 15, next. Run. And it just prints. So my random number generator is wrong. Why is it wrong? I generate, it's 1000 times a random number between 0 and 1 plus 1 converted to an integer. You know what? This doesn't matter. I don't know why I'm bothering using a function here. I can say 13 RV equals the int conversion of 1000 times random number between 0 and... Oh. Oh man, I changed my cursor color. There we go. Between 0 and 1 plus 1. Okay, now we're getting random numbers between 0 and 1000, or 1 and 1000, I guess. Okay, instead of printing what I want to do, or I guess what I want to print it, but then I also want to say A at I, or A at J should be equal to the random value we generated. And then will go next, and then we will have initialized. Goodness, we've initialized our array. What? List the first 100 lines. Oh man, lit. First 100 lines. Did I get rid of the 4? I got rid of the next 16 next J. Okay, so it'll create random values and then assign them. Beautiful. Okay, so why don't we do something? Let's fill A up fully. Okay, so we'll say list the first 15 lines. We'll fill A up fully. So for J equals 0 to 255, but we'll limit it to values between 1 and 100, right? So like, you know, we're surely we'll get a duplicate within that, right? Whatever. Let's list the first 100 lines again. So all right, so we've initialized our array. Okay, so what we're gonna do is we're gonna say for k equals 0 to 255. Loop through A, right? Oh goodness, we'll say the value we're working with is, or no, AK is really super short. It's a good one for my IRL friends. Shout out. They would have found that funny. But so okay, so we're gonna solve this with our hash map. So we'll start off by saying the before key, or the before value equals, or no, wow. So we'll start off, we want to get the value first. So we're going to say the input equals A at K. Go sub to what? Line 2000. Rem get the val 40. We want to say before value or no, we'll say next value. The next value should be equal to the get return plus 1. And then we'll say if next value is greater than 1, then go to line 200. And line 200 is going to print true and end. But otherwise, if it's true, then do that. Then we can just end it right there. But otherwise, we want to update the value in the table. So we'll say the input, low-key can still be A at K. So, but you know what? I want to be thorough. AKA, the second input should be equal to next value. And then go sub 1000. Rem put val in hash table. And then just keep going. next. And then if we get to the end, then I'll say 80 print false end. All right, that should be it. Undeft function error in 2010 list. 2010. Did I overwrite khash? Oops. Def function khash. I definitely did write it. Undeft function 2010 run. Undeft function error in 210. Gosh, list the first 100 lines. Def function khash k. Oh my gosh, does it not like our index value? Okay. Function you input x. Or you know what? Yeah, C is fine too. C for key. List 10. Run. Undeft function error in 210. That is so vexing. Why are you... List 2010 ki equals function khash with I. Run. I don't know why it's not liking that. Let's go ahead and list the first all of the lines that aren't in the program. So okay, line 3 has a definite syntax error. Because that's supposed to be line 30, isn't it? Okay. That solves something. So we dimension our variables, and then the hash table and the hash table input functions. We define our hash function, and then we make our input array. We populate the input array, and then for every element in the array, oh, where did that go? Oh well. For every element in the array, I'll say 30 before value equals a, or no, we're not getting the before I value. I'll say I equals a at k, and then go sub 2000, and then I'll say remark get val. Now run. Okay, so these are the values in our table, and okay, yeah. So at the top of the screen right now, there are 2 7s. All right, so we should get a false result, or no, a true result pretty quickly. How quick though? I don't know how fast it's gonna be because I don't know anything about collisions. I might go through and refill some of the hash table code with a bunch of print statements so we can like see what it's doing. Like in real time, I guess. But for now, let's just let it run and see if it works. Because man, it took so long just to run the code to get and put 2 values. Man, I'll have to do, wait, let's count. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Oh gosh, 11, 12, 13, 14, 15, 16. I think I'll have to go 16 because actually it's not 7 because I think that's 7 and 97. But luckily we have 77 and 47 right there, also close to the beginning. So, all right, I wish my code. That's hilarious. I wish it was showing more on the screen right now, because this is boring to look at. And I also don't know what's going on. So I hope that it's collecting stuff. Oh, Rue, true. It said true. It said true. Oh my gosh, that's so great. And looky here, let's flesh out the program a bit. List 88. List all the lines through 888. Okay. On line 17, by the way, I want to print a new line because it said Rue because the T was like the last character of the column. Just print nothing. Or wait, just to be sure, print blank. All right. What did I want to do? Instead of just printing false, true, and, why don't we put print false I, false, and then print I, end. Oh goodness, I'm in quote mode. False I, and oh, I'm in quote mode again. Oh goodness, oopsie. Anyways, list. Negative 888. Okay, now I just want to list 1000 through 1999. Okay, so let's do like 1021 print collision with key, and we'll print out, oh gosh, can I just throw stuff next to each other? Commodore 64 basic print. I can just throw stuff next to each other, right? Or do I have to do pluses? Okay, no need for a separate. We can just throw them next to each other like that. Collision with key, and I guess input. Key, or really, I want to say collision with keys, input, and H at K, H at 0, HT 0, KI. And, wow. My code is wrong. It's a very subtle issue here. There is a variable collision because for j equals 1 to 255, if ht ki plus j equals I, then go next. Then go next j. And then ki should be j. Because I is the input variable, and there's going to be a similar error at 2000. Wow, okay. How foolish was I? J, ki plus j equals I, and then next j, j. Okay. So I said collision with keys I and that. Then let's do 11, let's say 1198. And then we'll say 1198 print found spot for and it'll be I at ki plus j. And we can just run this and it should, so it's going to print out all the vowels, and it looks like it's going to be a while till we get, you know, a collision. Collision with keys 82 and 0. Interesting. 494. 24 and 0. Oh, this feels wrong. Oh gosh, what's happening? List 1000. Okay, so collision with keys I and the hash table 0 ki. With the key input and whatever the hash table is storing at the hashed input. List 1000 to 1999. And okay, I know, okay, the stream's almost gonna end. It's almost time for me to put stream away, but man, I'm committed to finishing this. Oh, it never puts the key in. It never puts the key in. Oh, okay. Oh, okay, that's devious. So we'll say 1205 in between 1200 and 1210. I'll say ht at 1 ki should be equal to k, or no, at 0 ki. So at the key table, it should be equal to the input, which is the key, or the first input, right, which is the key. Okay, so that's insightful. Okay, that's informative error messages right there. We could deduce what was going wrong. And low key, I might trim the range down to like 10 with keys 90 and 0. Okay. Found a spot for 90 at 486. 95 and 0. Oh my gosh, no, it's linear probing the whole way. Every single time it's linear probing, because list 1000 to 2000 or to 19999, because if ht is equal to I, then go to 1200. Here, if statements. Can I do like compound conditionals? If equation, if a 0, if a yada yada, if a logical operators can be used to combine several conditions. Okay, so beautiful. So if ht at ki or ht0 ki equals 0, then go to what, 1200. So it's having to like do a small probe operation every single time, because it didn't realize that the cell was empty. And remember, the range of values is only between 1 and 100. So really, it's good. And in fact, here, list 1000 to 1999. I want to say at 12:09, I want to print, put I, comma, I, comma, IA at KI plus J. And then I'll have to initialize J to 0 just in case. So I'll say 1001 PR equals I and J equals 0. Oh, 1001 PR equals I, J equals 0. Now run. Okay. So it's going to print out all our values. And every time it successfully puts an item in the table, it'll tell you put KV at array index. It should, at least. Okay. That's, oh, it should. That's weird. Oh, it's hashed. It's hashed. It's hashed. It's hashed. It's not. Okay. Oh, well. Wow. Array accesses are so slow. And you know what? I also, let's list 2000 onward. And let's say at line 2209 got print got I from KI plus J, and then list the first like 50 lines for K equals, let's initialize A to values in the range of like, let's start small, let's do 25. Run. So we're initializing numbers between 1 and 25. Okay, we have a duplicate, 6 and 6 on the first line. You can see, yeah, you can still see. So now it should be telling us, got 6 from 442, put 6 at 186. Got 21, put 21. Got 7, put 7. And this is right in line with our algorithm, which is like, oh, I didn't show you, but it's get the number, check if it's greater than 2. If it is, we're done. True. It got it, it checked it, and it's true. No freaking way. It just works. All right. Let's list the first 50 lines again. Yeah. Okay, so let's do values between like let's say 50. Let's make it take longer. Run. Beautiful. Oh wow, this is so fun. And let's look here. Can I overclock? Can I put you in turbo, or wait, no. List the first 1,000 lines, because I want to before the print statements. Or no, wait, it'll show what the duplicate is. Anyways, yeah, instead of going through the whole thing on line 20, why don't we just go through the first like 10 and hope we can trigger the true path, or the false path, I mean. So the first 10 values, 36, 19, 23, 16, 9, 2, 47, 29, 24, 27, 22. Okay, so there aren't any duplicates. And it only goes to the first like 10 values. So, all right, we're gonna wait for it to run. Man, Commodore 64 programming is kind of hard. Like, it's not easy, but it's at least fun. Like, I don't know. I've always found old computers very intriguing, and like, all right, this is gonna sound like cringe, I think, but I don't care actually. You know, I definitely have always considered myself like a programmer. Like, I'm a software engineer. I'm like a nerd guy. Um, Not in like a Sheldon Cooper way, in like a much cooler, suave way. Oh, okay, false, false. Boom. False. No duplicate. Okay, 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 okay. Oh gosh, that's foolish. List the first 50 lines. Okay, let's say, so we're going through 10 values, and then if it's not true or whatever, I want to hit the true path. So I guess we want, yeah, we just want like 5 values. Yeah, so okay, so it should trip it with the 2 3s there. But anyways, I don't know. I consider old computing to be almost like it's definitely like humanity's shared heritage. Like, you know, whatever old computer, true with element 3. Yes. Yes, it worked. Oh my goodness. Wow. Wow, wow, wow. Isn't that awesome? That's incredible. Oh my gosh, it just works. It just works. What line did I edit again? Oh, 50. List 13. Here. Let's do a nice 50 just to round it out. But yeah, so yeah, why do I care about old computers? Number one, I think they're neat. It's a technological challenge, but also, you know, on a more like personal level, I also find, I don't know, I feel like I'm pretty untethered. You know, I guess I'm looking for something stable, you might say. You know, I've done a lot, whatever, life circumstances aside. I'm like a software programmer guy. That's my like day job. That's my life. I've been doing this since I was like really little. Oh, hey, I already found a duplicate. Run again. I've been programming since forever, and I definitely consider that like old computers to be kind of like software engineer heritage, almost. Like, it feels like kind of cringe to say, but like, I don't know. This is like a cultural, almost like artifact of like my profession, um, really my identity, to be completely real. Um, and this is kind of like my heritage. It's like, I don't know, as an American, I've, wow, it already found a duplicate. 41. Yep, that was the first one. That's so funny that it's finding duplicates so fast. Well, you know, the program doesn't run fast, but the duplicates are being generated so soon on in the sequence. But anyways, yeah, wow, interesting. There's a ton of 38s on screen. I'm wondering, I wonder, you know, I'd be interested in investigating Commodore 64's random number generator, because it looks like a bad random number generator. But anyways, you know, like, there are certain things that are like within your like cultural heritage, like you know, I'm a Christian, right? The New Testament was written in ancient Greek. I've learned ancient Greek. Like I can read ancient Greek with like pretty good fluency. So for me, like that gives me an attachment to the New Testament, to the patristics, to the Septuagint, to like all these things. Oh, we only go through 10 values. Ha ha ha. List the first 80 lines. And you know, it's really funny how short the algorithm is. It's 1, 2, 3, 4, 5, 6 lines. And, you know, that's because we do multiple statements on one line. But, anyways, for k equals 0 to 2, 5, 5, space. All right. Now run. But yeah, that's it right there. Not only did we do neat code question 1, contains duplicates. We did leet code in Commodore 64 Basic. We also implemented a hash table on an 8-bit computer. So, you know what, if you were following along at home, pat yourself on the back. You know, you've done something that I'm sure has, what you've done is, I'm sure it was like a learning exercise for the true first generation of home computers. All right, we need more numbers available to us. It keeps landing on them so fast. The first 20 lines, because that's where all the A initialization there stuff is, isn't it? Let's go big. Let's go big. Let's say 500. Okay, there we go. That's a nice spread of numbers. But yeah, that's gonna be it. I really hope you enjoyed working on a hash table for the Commodore 64 with me, learning what a hash table is for the first time. Maybe that's you. Writing a hash table for an 8-bit processor and doing leet code on what, a 40, almost 50-year-old machine. That's pretty awesome. I'm gonna go ahead and let it play out. I'll say no, not section. I want, oh yeah, section properties, the Commodore 64 leet code. Low key, I'll just say bye bye. Bye bye. But yeah, I hope you enjoyed. There's going to be more Commodore 64 programming here on Code Orangutan coming down the aisle. I'm going to let this play out, see if we find one in this long sequence. I'll still be live, but I'm going to mute. It's consider this the end of the stream if you're watching. Or if you're watching the VOD maybe later. This is the end. Oh, and it found the freaking option. Okay, let's do one with 1,000. And then I'm going to go chill. I'm gonna play some Overwatch with my friend. It's gonna be rad. Or you know what? Let's go big. Shift backspace. 999. 1,000. Right. That's gonna be it from me. Hope you enjoyed the Code Orangutan. I've been the Code Orangutan. We've been doing primitive hardware, monkey hardware. It's been fun. I love Monkey Computer. It's really fun. And good morning, good day, good evening, good night, wherever you're watching this. I'm gonna go on mute. Bye bye. We can watch this finish out together, you know, in the background of whatever you're doing, maybe. Alrighty. It looks like it keeps finding the result much faster. I intended to leave this on for like 10 minutes or so, or however long it took. But anyways, that's gonna be it for the code orangutan. Thanks for watching.